thought that before we start today's topic, I'll just go over yesterday's L1 projection stuff in case things were not clear. Okay. So we were looking at subgradients and then subdifferentials and then the L1 projection. So the concept of subgradient was, I guess, fine to everyone, right? Supporting hyperplane. I think the trouble possibly was when we began to solve the projection on the L1 ball, right? So let's just go over it step by step. I want to make one small correction. Over here. So traditionally the signum function, okay, let me just make a note over here. Right, this is what I mean. This is when people say signum function, this is what they usually mean, the value of 0, right? Now in the derivation which we have done yesterday, the signum function has a different, what should I say, meaning. It's much closer to the subdifferential, which is -1 to 1. So here this will clear a lot of the confusion that we were having. So because of this, the graph of the signum function looks like, I use a highlighter. This is what the graph of the signum function looks like. Okay, so this is different from the graph of signum function which all of you are used to from signal processing, where signum of 0 is equal to 0 by definition. Here we have modified the signum function to be having a different behavior at 0. Technically speaking, this is not a function. Why is it not a function? Because it does not have a unique value at x equal to 0. It takes a range of values, right? So it's a generalization of a function. So this is what we mean by the signum function for this discussion. If it bothers you, you can call it by some other name, subdifferential version of signum function. Okay. Right. So then we looked at this L1 projection. The cost function, the Lagrangian became this, that was fine, right? And then when we began to take derivatives, that's where these various options come up, right? So if I write the L1 norm in this fashion, take the Lagrangian, dl by dxi is what I have to calculate. So I am left with subdifferential of mod xi. Okay. And here is where the various cases come into play. Okay. So all I am doing is I am taking this expression and I am taking different cases for xi. When xi is greater than 0, one by one these cases come up. The controversial or the slightly tricky to understand case was when xi was equal to 0, right? Now xi was equal to 0, this is the third expression over here that I get, xi minus yi plus lambda times subdifferential of mod x. And subdifferential, as we said, is any value between -1 and 1, okay? So when I move, keep xi to one side, move everything else to the right hand side, remember we have to always keep in mind that xi is equal to 0. That's the only case when this is valid. So therefore, I am left with yi plus, let me write it down. I am just rewriting this expression once again over here. Xi is equal to 0. This implies that yi plus lambda times subdifferential of xi equal to 0, right? We are just blindly substituting and seeing what comes out. So therefore, this implies what? That my choice of subdifferential is not, I cannot choose 0, because if I choose the value of the subdifferential to be 0, then I can't, yi is being given to me in the problem. Yi could be like -6 or something, right? Then this thing will not evaluate to 0, right? I'll get 6 plus lambda times 0, which is not equal to 0, right? So therefore, I have to choose the value of the subdifferential to be what? Minus yi by lambda, right? So I cannot choose, so therefore let me write it this explicitly in general, right? So that's what we have to keep in mind. And so when I wrote this in compact fashion over here, right? This, if you look at it a little bit more carefully, this use of signum x is the updated definition of signum. Then it makes perfect sense, right? Because now signum, when I substitute xi equal to 0, signum xi is not 0. It is the subdifferential and whatever it is, right? Okay. Then we sketch the graph, right? And then this entire range that I have over here, from what are the values over here? This was from lambda to minus lambda. In this entire range, xi remained 0 and yi basically was, I chose the value of the subdifferential to match yi. That's basically it. So this function looks like this. For yi less than minus lambda, I have the blue line. For yi greater than lambda, I have the red line, and in between xi remains 0. Okay. Once I have done this, the rest of all is just algebra. I just looked at this graph and I rewrote this in expression b. I need not have, but doing so, it just makes my algebra a little bit more convenient. Okay. And then we looked at a few just examples of how to use this expression that we got. So in this part, are there some points which are not clear? Right. So the only update is that keep in mind that this is our definition of the signum function that we are using. Yeah. At 0, we are going to let it be free, -1 to 1. Okay. Okay, so let's switch to, yeah. Mm-hmm.
Two gradients suppose at a point. So it's like linear combination or affine combination.
Yeah. I mean, it's a set of all vectors in between those two gradient values.
So it's like linear combination with coefficients all positive.
Yeah. You have to make sure, basically what is the test? Whatever linear combination you take, it should still be a supporting hyperplane. So the definition we had for subgradient, right? If you look back at this definition, here, this definition, this should hold true. So here you can substitute your value of gradient, right, and verify that this is happening. So for example, you can take alpha 1 grad f1 plus alpha 2 grad f2, substitute into this, come up with some relations on alpha 1, alpha 2. That's the way to do it. You should always go by the definition. Definition is supporting hyperplane. Make sure that your candidate G satisfies that. Okay.